Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, and welcome back to the Future Leaders in Quantum pre-hackathon webinar series. This workshop is the fourth installment in the webinar series leading up to the hackathon, which will take place starting May the 16th. This hackathon is open to everyone, and with 4 tracks to participate in, including art, education, innovation, and science, we think there will be an enjoyable and informative project for people of all backgrounds and skill levels. If you're enjoying these workshops and are excited for more hands-on experience, don't forget to head over to the AI for Good website or visit the Quantum Coalition website to pre-register for the hackathon. So today's workshop is for the innovation track, titled From Theory to Practice, Understanding the Quantum Technology Pipeline. We are honored to have with us Professor Chang Zhang, a researcher at the University of Science and Technology in China. Professor Zhang has made fundamental contributions to the building blocks of quantum communication technologies. These contributions include the experimental demonstration of a measurement device-independent quantum key distribution across a world record fiber transmission distance of 509 kilometers, realizing the first device-independent quantum random number generation, and implementing quantum teleportation over a metropolitan fiber network. He has also served as co-chair of the ITUT focus group on quantum information technology for networks. Today, Professor Zhang will give us a broad overview of these exciting real-world applications of quantum technology and more, and the engineering challenges that still lie ahead. Professor Zhang, thank you so much for being here, and the floor is yours.
Thank you, Ben, for your introduction, and it's my pleasure to introduce my field, basically the quantum information research field. So, okay, hold on. Yes, here. I would like to start from the Nobel Prize in Physics 2022. The 3 pioneers, Alan Aspect, John Clause, and Anton Zeilinger won the Nobel Prize in Physics 2022. This is very inspiring for the whole quantum community. And let's see why they get the Nobel Prize for experiments with. Hold on.
Could I stop you for just a second? Are you intending to share your screen?
Yeah, I didn't. I'm sorry. Yeah.
That's okay.
So you couldn't see my screen?
I can't, no.
Okay, let me share it. Okay, I saw it's already shared, but anyway. Let me check. Hold on.
Okay, screen sharing is working.
And then let me make it How about now?
That
Can
looks good.
you? Okay, cool. Okay, start again. So the Nobel Prize goes to the three scientists because the experiments with entangled photons, establishing the violation of Bayesian inequality, and the pioneering quantum information science. So here I will basically, so my talk will contain two parts. First part is the introduction to entangled photons and the violation of Bayesian inequality. And second part is talk about the quantum information science. First of all, to show how their work win the Nobel Prize, let me first make a brief introduction on the quantum superposition principle. As, as well known in our everyday life, a kite can only either be in a live or dead state. However, according to the superposition principle, a kite in the quantum world, it can even be in a coherent superposition of a live and dead state. But of course, here it doesn't mean a real kite. I'm talking about the a macro scale particle like a photon, atom, or molecule. It can be in the their state can be in the superposition state. And when we apply the superposition state into two photon or two particles, like then you get you get the quantum entanglement. Y- the superposition the state can be alive kite, and a dead kite and dead kite. This means like if we perform a measurement on the first kite, and if it is found to be alive, then the second kite will instantaneously collapse into the alive site, no matter how far away they are separated. So Einstein referred this phenomenon as spooky action at a distance. So physically, any two-level quantum system, it can be used as a realization of a qubit. For example, we can explore the two polarization state of single photons, horizontal and vertical, to encode one bit of information. For a system consisting of two photons, then they can be in one of the following Bell states. Let me, yeah, they can be in the Bell states. And then this kind of state is called a maximally entangled state. And what for the maximally entangled photon pairs, if you use the perfect correlation for measurement outcome of photon A and photon B, for example, if we have the entangled photons, we separated one to Beijing, the other one to Geneva or United States to our place, even the two measurement, and then we do the measurement. Even the two measurement are space-like separated, since Einstein believed that even the two photons they separate space-like, it still have the perfect correlation. So one can precisely predict the measurement result on particle B according to the measurement result on particle A. So in that sense, Einstein thinks that the outcome of a measurement cannot depend on any action in space-like separated regions. So you think quantum mechanics is a superficial, is a kind of is incomplete. There should be some real theory beneath of quantum theory. So he said there is a kind of reasonable assumption of local realism. There is a theory called the local hidden variable theory. It's beneath of the quantum mechanics. But for quantum mechanics, but for quantum mechanics, it's just believed that the individual state of two entangled particles are not identified. So the measurement outcome on particle A will not only determine its state, but also state of particle B immediately. So this is quantum non-locality. In 1935, we know that the story. Einstein published a paper is just saying that quantum mechanics description of physics reality be considered complete. And this one is also known as the EPR paradox. And later on, Niels Bohr, he also actually using the same title to see that the quantum mechanics is exactly the real theory, and you should believe it. And then there is a big kind of discussion between them, and also in the survey meetings. I think you all know you have almost all of us have seen this picture. But later on in 1964, there is a pioneer called John Bell in CERN. He proposed an experimental testable inequality by constructing an observable form from the measurement results of two particle entangled states. If the measurement outcome on each individual particles are predetermined as asserted by Einstein's local realism, the maximum value of the observable is 2. The result, if you do a kind of many runs of experiment, the maximum you can achieve is 2. But if it's quantum mechanics, if it based on quantum mechanics, the measurement outcome on each individual particle are not identified initially. The maximum value of this quantity can reach 2 times 2 times square 2. So it can go to a 2.8, something like that. After that, there are many famous experiments. For example, the first Bell experiment by Friedman and Klause in 1972. And then Alan Aspect in 1982, he used the fast switch controlled by preset quasi-periodic signals. And later, Anton Zeilinger group in 1998 using the random number generator to do the space-like measure the entangled photons. And then Wineland group in NEST, they closed the detection loophole. And then Rona Hansen, Siu Nam, and also Zelinger's group, and also our group, we close the both detection and locality loopholes. And for all this kind of experiment, the result is more than true. So in the sense that at least for the Bell test and the quantum mechanics is correct, and then they beat the local hidden variable theory. It's right, but still there has some loopholes, such as freedom of choice loophole and the collapse locality loophole that need to be addressed further. There's still some scientists believe that we still address some loopholes. So that's the condition. But anyway, for the three pioneers, Clauser, Asbecht, and Anton Zeilinger, they got Nobel Prize because of these pioneering experiments. And then because the violation of Bell inequality implies that the quantum world is intrinsically random. This is because for entanglement states, before the measurement, even the God does not know what the measurement result will be. Even the God doesn't know the result is, so it's unpredictable. So in that sense, an immediate application of quantum entanglement is in device-independent quantum random number generation. By which the true random number can be generated where the loophole-free violation of Bell inequality, even with the suspect devices, is called the DIQRNG. And you can see in 2018, our group and the NIST, we both implement the DIQRNG. And then it could find various applications, numerical modeling, artificial intelligence, cryptography, and so on. And
Professor Zhang, can I stop you ask a quick question?
Sure, go ahead.
So I think I'm clear on what the locality loophole is, but could you talk a little bit more about what you mean by the detection loophole?
Oh, basically it's actually in most of the scientific experiment, you have assumption is called a fair sampling assumption. Means like you generate some particle, you generate entanglement for the pairs, and then you detect it with your detector. You collect it into single mode fiber and detect by your detector. In the sense, for example, if you generate about 1 million photon pairs, but you can get about in general you can only detect about 100K photon pair clicks, but you believe that it's fire because you think you just choose some reasonable, you have assumption. You think that for the 100K photon pairs result, it can represent the whole thing. But some scientists think, okay, maybe there is another way, means like, for example, for the 900K photon pairs, it doesn't violate Bell inequality. And exactly the 100K you captured, it violates Bell inequality. But if you take all the thing, then you will find, okay, it doesn't violate Bell inequality. You just choose something violating Bell inequality. So this is called the detection loophole. And actually, it's not only some paranoid thinking, because people can using some detection loop code can attack your system to fake the Bell inequality. Means like we can show that if you can only collect not the enough bottom pairs, the Bell inequality cannot you can fake a kind of a Bell state violation. Yeah, that's the basic idea.
Okay,
Okay,
thank you for
then
explaining. I appreciate it.
cool. Then I go ahead. So another important application of the Bell's theorem is the entanglement-enabled secure communication proposed by Arch Eckert in 1991. And the basic idea is you use the entanglement pair generate a random number, and if you distribute it to the two remote users, and these two remote users can use this random number as k to encode your information, and this is called quantum k distribution. So it's very simple. But in the absence of the eavesdropping, the entanglement will not be disturbed. So the maximum value of S can reach 2 times square 2. But if there is an eavesdropping, unauthorized measurement will leave state photons identified. So the value of S cannot exceed 2. So in the sense, people using this one to do you first generate entanglement and distribute to Alice and Bob, and they generated a random number as their K. And sometimes they using that one, they test the Bell inequality. If it violates the Bell inequality, they say, okay, this is it's certified randomness is certified K. But if it cannot violate the Bell inequality, they say, okay, must be a eavesdropper. So this is the basic idea for quantum K distribution. And then, of course, if you use loophole-free Bell inequality, you get the called device-independent quantum K distribution. And this experiment is being done in 2022 by our group, Oxford, and Max Planck Institute. Anyway, so I think I gave a brief introduction of the Bell inequality. And then interesting, besides the discovery in the quantum foundations, from the test of quantum non-locality physicists, because people want to try to test the quantum non-locality, test the Bell inequality, we have developed the groundbreaking technologies for coherent manipulating the quantum system to generate in single photon, generate quantum entanglement, to deliver, transfer the quantum state, and manipulate the quantum state, and then to measure it. So this kind of technology actually lead to the emerging quantum information science, including quantum communication, quantum computing, and then quantum metrology to do and you can get the unconditional security, computational capacity, and also the precision measurement. So I will then introduce the field. Okay, I would like to even I'm doing the quantum communication, but I would like to start from the quantum computation because it's the hottest field now. And then for quantum computation, it uses quantum bits to encode the information, which can be in coherent superposition, and the information represented by them can be processed in parallel. Which means like here you can see the classical bits, and here is the quantum bits. If we have a if we have a three particle for the quantum state, for the quantum superposition of a three particle, it can have about 8 state for 3 quantum bit, it can represent 8 state. And you can imagine if there is a 10 photon or 10 particle for 10 qubit, you can get for just one state, it can represent about 2 times 10, about 10,000, about 1,000 kind of possibility. And then if you use this one to do some calculation or computation, it can result in exponentially speed up in the principle. But of course, it's not that simple, but I just give you how it can be a parallel computation, the basic idea. And then there are not too much, the very useful quantum algorithm, but the most famous one, maybe is the Shor's factoring algorithm. One can efficiently factorize large number and break the public key encryption system. For example, if you want to factor a 300-digit number with the classical supercomputer, you need about 150,000 years, but use quantum terahertz computer only 1 second. But of course, quantum computer is very difficult. I'll tell you later. But Anyway, so it has a huge potential. So it can be used in the code breaking, and also in future some application like weather forecast, financial analysis, and drug design. A lot of things. And then let's go to if you want to let's go to the roadmap of the quantum computing. There's supposed to be a three milestone. The milestone one is I mean before when I was a PhD student, when I was a student like you, like Ben, we are still in milestone zero. Means like at that time we don't know whether quantum computation can work or not work. We only know quantum K distribution works, but we don't know quantum computing. But just very recently, now we have three milestones. I'll tell you. The first one is the quantum computation advantage. It means like you do some useless work. You're just beating classical supercomputing in specific tasks. It either useful or useless. But unfortunately, all the current quantum computation advantage are all in useless kind of work. But the speed up is very overwhelming, huge, that no classical computer can perform the same task in a reasonable amount of time and is likely overtuned by classical algorithm or hardware improvement. And this is called the quantum computation advantage. And the milestone two is the near-term application. We are now in the near-term application now, currently. We are in the milestone two, the quantum simulator, to efficiently mimic the evolution of a complex quantum system, like the high temperature superconductivity, etc. And also in this kind of near-term application, people should work on the error correction. We should do a good error correction, and then when we can get a very good error correction, then we can go to the milestone three, called the universal quantum computing. It's a universal programmable quantum computation with help of the quantum error correction. In that sense, in that area, you can correct the public key system. So we are still in here, which means, and you may ask how many years we can go to here. I think many pioneers have given I forgot that guy's name, the president of IMEDA, Dr. Huang, about 10 to 20 years. I agree with him. I think probably 10 to 20 years, we probably can go to universal QC. It's also confirmed by the leader of our center, Jianwei Pan. He also think about 10 to 20 years. I think basically the reasonable scientists think it will be that time. Yeah. Anyway, I will first introduce about the quantum computation advantage. Here, I would like to compare the quantum computation advantage with the Bell inequality, the first topic I talked today. For the Bell inequality, it's the non-local correlations and the intrinsic randomness. It cannot be simulated by any local hidden variable. So it refutes the Einstein's local realism, right? And also for the quantum computation advantage, a complex quantum process, it cannot be efficiently simulated by classical computers. So in the sense, it refutes the extended Turing thesis. The classical computer can simulate computational power of any physical process with polynomial overhead. For quantum processor, it couldn't. So that's the thing, I think. That's why we think it's important. And there are actually candidates for the quantum computation, the original photons, the superconducting. Now Google and IBM is working, and also we are working on that, ultra cold atoms. This one and also atomic arrays. This one is not very popular. I think Michelle Lukin in Harvard is working on that. And the Trip9, we have InQ, we have the many good professors work on that, and also solid state. This area people are also working very hard, like in Australia. And also there is another one is by Microsoft is working on the topological. This one is super difficult, and then uh, until now there is no any single qubit from the topological quantum computing, but it has potential. So there's it's still several ways they are competing. Not like quantum communication. We just use photons because photon is designed for communication. Yeah. Anyway, and then let's see. The first computational advantage is done by Google. The very famous the SECMA. It's a 53 superconducting qubits. It's announced the quantum supremacy in 2019. Although later on, a Chinese scientist, my colleague, Pan Zhang, he mentioned that he can using some classical algorithm can simulate the Google's computer. But later on, of course, this one is Google's computation is still exponential. So if you put more qubits, then you can easily beat the classical algorithm. So. And then in China, we have the 主冲之. It's named 主冲之 2. It's a 主冲之 is a Chinese scientist in ancient China. He successfully calculated the seventh digit of the pi. But anyway, he's old guy. And then we just use his name, we follow his name, and then produce the superconducting processor. And then we observe the strong quantum computation advantage using a 66 qubit superconducting quantum processor. And then it's about 6 orders magnitudes more difficult than SIGMON. But of course, there is still computation between Google and us. The very recent result is Google this year, the beginning of this year, Google get their first their quantum processor called Willow, and then they do some huge quantum advantage. And for the China side, my colleague Xiaobo, he get the 主冲子 3, means like they are in also the same level. So this is good computation. Yeah. And then we have the photons. With photons, my colleague Chaoyang Lu, he get the 9张 optical. He also shows the strong quantum computation advantage using photons. And uh, the task he is doing is the Gaussian Bosonian sampling. It's still a useless task, but in this kind of task, he shows the quantum advantage. He already shows the 9张 3. It's about 10 to 16 times faster than classical supercomputer. But it's just number, because it's exponential. So now he has a 9张 4. I forgot the exact number, how fast it be, but it must be faster, much faster than this one, but still. And also, I know that in Canada there is a company called hmm, I forgot that name. Xanadu. They do the quantum advantage, but they are using the cheapest one. Not they are using the integrated photonics and to show the quantum advantage. But it's slower than what Chaoyang did, but it's integrated one. But still, for no matter Xanadu or my colleague Chaoyang couldn't find some real quantum application yet. We are still in a kind of field that to find some useful quantum computation task. We are still in that area. And very recently, I noticed that a company in United States called doing the tripwire, I think is Quantinuum. Yeah, they also saw the quantum advantage using the tripwire. Yeah, that's the whole story. That the main players who has shown the quantum advantage. But still, we are still waiting for a real killer application of quantum computation. It'd be useful. We are still waiting for that. And also Google is doing very good. Is doing very good in error correction, and we are also working on that field. So I think maybe the next step, if the error correction is been done, then we can expect the universal quantum computing. Yeah. So if the real if the real useful quantum computing, if the universal quantum computing is done, what the first task will be? The first task will be crack the public crypto the public key system. So in the sense, you need to worry about your vibers the you need to worry about the security of your internet. So in the sense that because the topic of today is quantum for good, right? So if the quantum computing is made, it can crack the public key system. Then how can we do? There are actually two ways. One way is using the quantum communication with the quantum key distribution, just like what I mentioned, using the quantum method to share the key. And even the quantum computer couldn't, even the universal quantum computer couldn't crack the quantum key distribution network because it's not based on some difficult problem like the factoring big number. It's based on the basic principle of quantum entanglement or quantum mechanics. And the other one is the post-quantum. It's also some it's also some based on some kind of mathematical hard problems. There are several candidates. I think NIST is working on that. They are organizing the kind of selecting the algorithms, but still it's based on the kind of complexity, computational complexity assumption. So I'm not quite sure about its security. So there are two ways. So in the sense, there are many countries are working on that. And then because I'm not expert in the PQC or post-quantum things, so I will basically talk about the quantum key distribution. And then the basic principle is based on Shannon's idea that if the Alice and Bob, the two communication parties, if they share the random number, and then they use the random number to encode their information one by one, it's called one-time pad, then you can get the unconditionally secure. The problem is how can we share the random number? Just as mentioned, you get in quantum entanglement, you share between them. Or you use single photon and you share between Alice and Bob. And recently people find even you can also using the weak coherent state, means like laser pointer attenuate into single photon level and then send. It also works. There are many theoretical and experimental efforts on that. No matter what, we can see is from the first idea is proposed by Charles Bennett and Gilles Brassard, and also the Arthur Eckert, as I mentioned. And later on, there are from 1989 about 32 centimeters, and later on till to our lab in 2 years ago in 2023, we already do 1,000 kilometers in the lab. So yeah, so that's the basic idea. And in the field, we get about 500 kilometers without any relay in between Jinan to Qingdao. And also,
Could
go
I
ahead.
ask you a quick question, actually?
Sure,
So
go ahead.
you were talking previously about with Bell inequality tests that you have this detector loophole because you have, you can have like in some, I guess in some platforms, relatively low counts, like a low number of photons actually get detected. So how do you do quantum key distribution with single photons, and especially over a long distance, when you can only detect a small fraction of transmitted photons?
That is a very good question. So because the people, if you don't trust your detector, if you don't trust your source, so if you want to trust, you don't trust anything, then you do what you can do is just you use the loophole free Bell test. And then if you get violate Bell inequality, and then you get secure. That one is called a device independent quantum key distribution. That's the most secure quantum key distribution, but it's useless. As you mentioned, because you can imagine it can only go to about 100, it can only go to about 20 or 30 kilometers. That's the most. So then what was the solution? Okay, in general, for quantum key distribution people, in general, we trust our source, we trust our detector. We only give the channel to the eavesdropper. We don't trust the channel. Anyone can work on anything on the channel. So what our task is guarantee the channel security. And sometimes, if you don't trust your detector, okay, we have some called measurement device independent. Means like you need not trust your detector, but you need trust your source. And sometimes you trust your source, you use source independent QKD. But if you don't want to trust anything, then it's just device independent. That one is too difficult. It's still after the range of the research. if of the range of application. So currently, people using the trustful QKD means like you trust your detector or trust your provider. But in general, it's just like you trust your bank, something like that. If you trust your provider, and you just guarantee the security of the channel. So QKD is basically is guaranteed the channel security. Somehow it couldn't fix the problem of the security of your physical device in your lab or in your at home. So it couldn't fix the problem that the device at your home it doesn't work. It put in it has some backdoor. That one doesn't work. Yeah. Okay.
Thank you.
So yeah. And then we launched a satellite in 2016. It's called Mishes, also another Chinese, the scientist. We do not have too many scientists in old China, but this one is a good one. Yeah. He observed the first the light goes through the line, some straight line, something like that. And then we do a lot of kind of quantum key distribution by the very early time. And then there are many not only China. I'm sorry. Sometimes because I have limited time, I only talk about what we are doing. Actually, it's all over the world. I mean, in Europe, many people are doing the fiber QKD. But I'm sorry, not in US. US people, I don't know, didn't do too much on QKD now, although it's invented in the United States and Canada. But anyway. So there is a quantum communication project in the space. We have the Singapore's one, and also the Israel one, and Canada one, Germany one. And very recently, I heard that the Boeing, the U.S. air company called the Boeing, they also want to do some entanglement swapping or entanglement things on the satellite. That's what I heard. And very recently, we because the mission satellite, the payload is about 100 kilogram. It's cost about zero point 0.3 billion Chinese yuan for the whole project. And now we have a small one called the Jinan 1 microsatellite. It only weighs about 23 kilogram. And then, but the performance is actually much better than mission satellite. And this one is only cost about 20 million Chinese yuan. You can consider about 3 or 4 million US dollars, something like that, for the payload. So and then this one is just recently published in Nature. You can download the paper if you're interested. Means like, and now we can reduce again, reduce further the price of the payload and make it smaller and make it more efficient. Technology changes, something like that. And now recently we have in China, we have Mishes, we have the Jinan one, and we have actually a fiber network in China. It's about around 20,000 kilometers in China. And now we want to upgrade it to make it can transfer the time, not only do the quantum key distribution, but also transfer the time and also to do the fiber sensing. So that sense, we build up a network of China. So you can check this paper if you're interested. And then, okay, go back to the Nobel Prize. They do the Bell-State measurement, and then they open the door for the quantum communication and also quantum computation probably. So that's why you can see in the Nobel Prize they mentioned the Mission satellite, the this one. Yeah, this is what happened in the background kind of scientific background announcement, and they talk about that. Yeah. So okay, I have about 5 minutes. So I want to go to the quantum metrology. There is a broad field. It's not like quantum computing or quantum key distribution. They have very specific task, important but very specific. But for the quantum metrology or quantum precise measurement or quantum sensing is a very broad field area. You can use it for everything. And then I only talk about the one example which I'm involved. It's a redefinition of the international system units based on quantum way. It was decided in 2018. Means like the SU units for the eight for the 7 units, about 6 is related to quantum or related to fundamental constants. And here I would like to take the second. because the second in general is the most the time is the most precise measured unit in measured units in all these units. So nowadays we use the season, the microwave clock to decide to definite the second, and then the uncertainty is about minus 16, means like about a billion years it doesn't change 1 second. But if you use go to the optical clock, I mean the best optical clock is in Jela, you know that, right? By Junye and also other researchers, and they can go to actually not only minus 18 but also minus 19. It's about maybe 100 billions, maybe 1,000 billion years. It doesn't change 1 second. So in the sense, people are now thinking to using the optical clock, cold atom or triple ion optical clock to replace the kind of to replace the microwave clock. So so in the sense, China has a plan. I'm involved in the plan to launch the new satellite to put the optical clock in the satellite, and then to compare this satellite, this clock with the clocks in our world, the clocks, and then because if you want to redefinition of the second, you need to have several institute has the good optical clock, and you also need to compare them. And for the microwave clock, you use a GPS, you use microwave to work on that. But for the optics, for the optical clock, you need using laser, you use frequency comb to compare of them. And that's what we are doing in 2027. That's our plan. I heard that NASA or NIST may have the plan for the maybe in 2029 or 2030, something like that. But anyway, I think it's a very good kind of I think we should do some international collaboration, but I'm not quite sure about what's going on with the condition. And also for this kind of frequency, for this kind of comparing of the clock, it has also many applications, not only for the redefinition of second, but also the secure communication, and also you can use it to do you can use it to do the gravitation test, the dark matter search, the precise navigation. There are many kind of applications if you can do that. Okay. Oh, and then about the standardization, because it's organized by ITU, so I should talk about some standardization things, because I definitely it's very important, because quantum things is a kind of a new things, but if you want to make it if you want to do a free market, if you want to do the international collaboration, you definitely need to standardize that. And also, if you want to do the quantum for good, you should have some kind of basic kind of agreement. That means like if your quantum computer do not crack other people's public key system, something like that. I don't know. I'm not a politician. I'm just saying probably we have to talk about that. We need to think about that. But anyway, from 2008, ETSI initiate has some kind of international kind of standardization things, and IEEE, SOAC, ITU. And here I would like to mention the ITU in 2019. It's just before the COVID. And we have the FT focus group on the quantum information technology for network, focus group. And then it's the first one is in Jinan. And I was here with ITU colleagues, and also Jillian as our secretary. But unfortunately, this one, I mean, good thing is we released about 9 standards in we released the summer standards, and also for the whole group, we submit about more than 9 technical reports, and some is now already became the standards of ITU. So I hope that in the future that there will be a new study group on quantum, but probably I hope so. That's all about the technology aspect. And the future, we hope that we have the satellite kind of constellation, and then we have the network, And in each network, we have a quantum computer as the processor. We have the quantum sensor as the to sensing the information, and then using the quantum network to distribute it. And then with future will be the quantum internet. That's what I'm thinking, and we're hoping. That's it. Thank you.
Professor Zhang, thank you so much for that great talk.
Thank you.
If it's all right, I have a few questions to ask that I think might be interesting to the audience.
Go ahead.
Okay, so first, you've shown us some powerful examples of what's possible in sensing, communications, metrology, especially with these projects in China. Which of these areas do you think will see the fastest real-world deployment globally? And what will it take to scale this beyond just like pilot projects?
I think the latest, the last one to be practical will be quantum computation. That's for sure, because it's so difficult. And for the quantum communication and the quantum metrology is different, two things. For the quantum sensing or metrology things, because here we are talking about quantum information science. But you all know that for the atomic clock, it has been used about maybe 30 years or maybe 40 or 50 years, because that one is actually we if you talk about if you include that one, I think the quantum sensing or metrology is the first one. It's already there. But if you talk about the quantum information or quantum enhanced things, I think probably the quantum communication, because in China there are already banks or other kind of or other companies, and then we already use it in a cell phone. But of course, it's just using quantum random number inside of it, and it works. So in the sense, I think quantum communication may be the first one, and the quantum enhanced, like the gravity measurement, the atom interferometer to measure the quantum gravity, and also the optical clock, and maybe but yeah, it's kind of. I think that's what the status. I think the quantum metrology and sensing and the quantum communication, they are all under the application. Yeah. It depends on how could you define under application. Is to government or to business or to people. If to people, I don't think every quantum can go to people. Maybe some random number generator, because you can use it for lottery. Yeah. Otherwise, it's basically still for business or for big company or for government, something like that.
Mhm. That makes sense. So you mentioned that like quantum computing is the hardest. Like how do the technological challenges for quantum networks and quantum communication differ from those for building a quantum computer?
Ah, I think is I think for quantum computer, I think the most difficult part is scalability. You need to do also the error correction. You need to do you need manipulate, for example, 1,000 qubits, and each qubit, their error should be about their fidelity of the qubit, the operation of the qubit should be 4 or 5 9, means like 99.99 or 99.999% fidelity. That's too difficult. So in the sense, you need using some redundant qubit, physical qubit, to encode a logical qubit. For example, you probably need to use about 1,000, for example, 1,099.9 qubit, physical qubits, to encode a 99.999 logical qubits. And then you need about 1,000 logical qubit to do a quantum computer. That's why it's difficult. And for for QKD, for example, you do not need such high fidelity. And then what you need to do is you do your laser, and as long as its error is about, for example, 2% or 3%, goes through some 100 kilometers, and the error is about 2%, 98, it still works. And you can distillate the case. So that's why it's easier. Yeah. And
Thank
you
you.
only need single qubit.
Mhm.
You do not need multi qubit.
Yeah, I think a lot of people working on quantum computers would be thrilled if 98% error were tolerable for performing a quantum computation.
No,
But
98% is rubbish. Just make
yeah,
fun.
um,
Just make fun for quantum computation. If you tell people what you are doing is 98% fidelity, doesn't work.
mhm. Um, so I also wanted to ask you, you talked a little bit about some like near-term demonstrations of quantum advantage from the Sycamore processor and the Zhuchengzhu, I'm sorry if I'm pronouncing that wrong, processor in China. And I wanted to ask, like, could you maybe talk a little bit like non-technically about what kind of task the quantum computer is performing and how that differs from what you call like universal quantum computation?
Oh, for example, let me see the boson sampling. I don't know. Do you know the boson sampling?
Yes.
The I think boson sampling is a very good idea to tell you how it works. Means like for the classical, you have a ball, and it goes through many kind of branch, and then it's classical. It's just classical sampling. Means like you have a ball and then go through many kind of carts, many road. But for quantum is like you have many input, and because each one they interference with each other. So just measure, just tell what's the interference result after, for example, if you input about 100 photons, then what will happen? But then, and for that one, if you use a quantum computer, like if you are just using the quantum photon to do that, or you use a single photon or use the square state to do that. It'd be faster than calculate just using the classical computer. So that's the thing. It's just toy. I mean, you couldn't find what's the real application for that, but yeah, that it is. I think that I think till now, I think for all this classical, all this quantum advantage is doing such kind of thing. Means like you find some spatial algorithm, quantum is definitely has advantage than classical, and you do that. Yeah.
Okay, that clarifies it a lot. Thank you. Um, so I think you'll be interested in talking about this. So you've said a lot in the context of the quantum rendered number generation, quantum key distribution, this word device independent. I was wondering if you could maybe talk a little bit more about what makes it device independent and why that's a desirable feature.
I should say for the device independent things is like in general it's not very useful. I should say. I should say that in general, when we want to do some security things, in general, we trust something, right? You trust for example, you trust you trust your bank, you trust your provider, and sometimes like that. That one is very efficient. But sometimes, if you don't trust anyone, and then for that's the device independent things work. So the device independent quantum key distribution is not useful. For the device independent quantum random number generator, we are just thinking use that one for a standard or for a beacon. That's what I'm thinking. It's a kind of certified randomness. Even you don't trust it. If you don't trust the vendor, and then if you test, you can test it. So you can test the building quality, and if it works, then you trust this one. So in the sense, you need not worries from China or from anywhere. So that's the and it's good for standardization. So that's why I'm pushing this one to uh, to do a standard for random number because it's highestly secure random number generator. So it can be a standard. And the good thing is we have one, and also United States NIST has one. We are the most leading kind of research institute to do that one. And actually, it's between 2018 is possible. I have discussed with my friend Steve Nam. He has passed away about years ago, 2 years ago. Yeah, but he is a very good scientist. And we discuss a lot about the how I do a beacon in China, device independent. They do device independent random number generator, and then someone, for example, in Europe, they don't trust. Some people don't trust me. Some people don't trust Sewu, but they just download random number and they do XOR. And this random, as long as one is a random number, then it's a random number. So it's and it's also kind of China standard, United standard. So I think that's a perfect kind of application of the perfect example for the quantum things, for the trust things, for the standardization things, and also yeah.
Okay, thank you. I have just one last question, but one last question before we wrap up today.
Go ahead.
Could you maybe talk about, so for hackathon participants who are doing the innovation track, they're going to be thinking about cross-sector, cross-field applications of quantum technology. Could you maybe give any advice you might have for those participants about starting their projects?
It's a good idea. I don't know. So I can think about that. For example, think about how could you use your quantum random number. For example, my colleagues in China, they use this such a earphone, and they can encode they put some random number inside of it, and then they can but it's a Bluetooth the kind of earphone. And when you open when this one is connected to your phone, and it can provide some random number encoding the kind of how can I say it can provide some random number and can help you encode some message in your application, in your app. And for example, if you are using the WhatsApp, if you are using Zoom or whatever, if your text message, it can provide a quantum random number and encode it. So and this one is shared, of course, with your provider. So who is selling this one? You need to trust them. But that one, then you and your friends will using it. So that's one application for random number or for quantum gate distribution. And for the sensing things, it is more like related to the government or business. For example, if you want to sensing the earthquake, sensing the for example the gravity, yeah, just think about if you're sensing any physical quantity, and if you use quantum, it can be more precise, something like that. I don't know. And for quantum computation, it's still in an area that no real kind of quantum speed up application. But there is some quantum inspired algorithm. People think about if you think about in a parallel way, you can probably find some way that can speed up, but not not exponential, but still has some speed up. For example, you use a coherent Ising machine or other things. That's also what my friend in the United States and Japan did. So yeah, but it's still not useful for everyday's life. So
Mhm.
yeah, but
Yeah, still a ways to go on that front. Well, that's a wonderful answer. Thank you so much. I guess it's a good time for us to wrap up. Thanks for joining us again. We're really honored to speak with you. To our
me too.
audience, we look forward to seeing you again soon with our next pre-flick workshop called Playing with Possibilities, Teaching Quantum Through Chess. Don't forget to check back for more updates on our website, which is quantumcoalition.io, and pre-register for the Flick Hackathon taking place this May. Thank you so much for listening, and we hope you have a great day.
Bye bye.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.